By 1975, humanity had built an industrial empire on the back of massive centralized electricity grids. We had tamed supercritical steam, unlocked the power of the atom, and wired the globe with towering extra high voltage lines. But the foundations were shaking. The 1973 oil crisis exposed a brutal reality. The global power engine was deeply vulnerable, rigid, and heavily reliant on fossil fuel baseload plants operating at thermal efficiencies that rarely crossed 35%. As the world entered the final quarter of the 20th century, a new era of engineering was born. Over the next 50 years, the grid would undergo a radical transformation, evolving from a rigid analog machine into a dynamic, intelligent, and decarbonizing ecosystem. This is the story of how we powered the modern world between 1975 and 2025. The first major breakthrough of this new era did not happen in a laboratory. It happened inside the combustion chamber. Desperate for fuel flexibility and rapid deployment, the power industry turned to heavy-duty industrial gas turbines, borrowing advanced metallurgy and cooling techniques from aerospace engineering. Engineers pushed turbine inlet temperatures past 1500 degrees Celsius, using single crystal superalloys and specialized thermal barrier coatings to survive environments hotter than the melting point of the metal itself. But the true game changer was the commercialization of the combined cycle gas turbine, or CCGT, in the 1980s and 90s. By capturing the blistering exhaust heat from a gas turbine and routing it into a secondary steam turbine, engineers did the unthinkable. They shattered the long-standing thermodynamic glass ceiling, driving plant efficiencies from 35% straight up to an astonishing 60% and eventually breaching 64% by the 2020s. While gas turbines were rewriting efficiency records, the nuclear sector was facing a profound crisis of confidence. High-profile accidents at 3 Mile Island in 1979 and Chernobyl in 1986 forced a massive regulatory and philosophical shift. The industry had to pivot from raw scaling to absolute inherent safety. Enter Generation 3 and 3 Plus designs. Engineers pioneered passive safety systems that eliminated the need for human intervention or emergency electrical backup power during a crisis. Instead, these systems relied entirely on the unshakable laws of physics, using gravity, natural convection, and compressed gases to safely cool a reactor core in an emergency. By the early 2020s, the nuclear frontier shifted again with the rise of small modular reactors, or SMRs. These factory-fabricated flexible units meant nuclear power could finally move away from multi-billion-dollar mega projects and step into the modern world as an agile partner for local grids. While traditional plants were optimizing, a quiet revolution was gathering strength on the margins of the grid. In 1975, solar panels and wind turbines were dismissed as niche experimental novelties. By 2025, they had become the cheapest source of new bulk electricity on Earth. Wind power scaled up at a breathtaking pace. The modest sub-100 kilowatt onshore wind turbines of the 1980s evolved into towering offshore giants exceeding 15 megawatts, with rotor diameters wider than the wingspan of multiple jumbo jets. Simultaneously, solar photovoltaics underwent a manufacturing scale-up of historic proportions. Advanced materials science drove traditional silicon cells out of the lab and into the mainstream, introducing high-efficiency PERC technology, bifacial panels, and tandem perovskite layers. Commercial panel efficiency skyrocketed, while the cost of solar power plummeted by over 90% in just a single decade. But generating this immense volume of clean, weather-dependent power created a massive problem. How do you balance a grid when the sun goes down and the wind stops blowing? The old unidirectional grid of 1975, where power simply flowed from one big plant to a passive consumer, could not survive the 21st century. The transmission network had to become smart. High voltage direct current, or HVDC, became the superhighways of the global grid. Equipped with advanced voltage source converters and modern power electronics, HVDC lines began moving massive blocks of power across thousands of kilometers and under vast oceans with minimal losses. At the local level, the grid was injected with digital intelligence. armed with FESOR measurement units, real-time SCADA systems, and massive utility-scale battery energy storage systems. Grid operators began doing what was once considered impossible, balancing volatile renewable energy inputs second by second, ensuring grid stability across entire continents. In the 50 years between 1975 and 2025, humanity did not just build more power plants. We fundamentally re-engineered the lifeblood of modern civilization. We moved from an era of raw combustion and isolated rigid systems into an interconnected, highly digitized, and rapidly decarbonizing global matrix. The 50-year fuse that was lit in the mid-20th century has culminated in the most complex, intelligent machine ever built by human hands, the modern power grid. And as we look to the future, the journey toward a fully sustainable, electrified world has only just begun. For more information, visit www.globalpowernews.com or my YouTube channel at Nawas Laco Power Pro. Do not forget to subscribe, like, and share.